we get to the do, we want to show at least the first and last calculation or component of the chi-square calculation, right? So, my observed minus expected for type A, okay? How many type A people did I observe in my sample of 150? Was it 13? Look at your list. I don't have my calculator handy. Yes, I do. Observed, we observed 13. Okay, so I'm going to say take 13 minus the number I expected, 63. Whoa. Square that quantity and divide by my expected. 13 is how many in my sample of 150 that I took, okay, that had type A blood.
Where is this?
Remember I said I copied your examples after I decided to do this example. So you don't have it on that paper.
That would make more sense.
Sorry. Okay. It's from this table, right there. Okay? Sorry about that. No. Does it?
I think someone said 13 looking at the birthday problem.
50. It says 50.
That makes more
Oh, there you go. Thank you.
Blows.
I have the wrong data in my calculator. 50. Okay. The last type of blood that is displayed here is type O, and we observed 67. So I'm just going to do plus, dot, dot, dot. And then I'm going to do my component for the type O blood. So observed is 67. We expected 66. Square that quantity and divide by that expected. Okay? So this is the minimal amount of work, or minimum amount of work that I want to see in your do. Okay, we are going to let the calculator get the rest for us. Okay, so clear all your lists if you will a sec, and I'll read off those observed counts for you here again. So here they are. In list 1, type A, 50. Type B, 23. Type C, 10. And type O, 67. Okay. Our expected we have recorded in our do. So our expected, we expected 63 type A, 15 type B, 6 type AB, and 66 type O. Okay? So I have stored my observed in list 1 and my expected in list 2, which are not the same in this case. We're not looking for an even distribution. Nate?
In your plan, did you say that you possibly don't have 5 categories?
It's not about the number of categories.
Oh,
It's about
the
the
number
expected
in the
counts
category.
within each category.
That makes more sense.
Good. Okay. All right. So we've got all those stored, right? So let's go ahead and run our goodness of fit test, chi-square GOF. L1 and L2 don't need to change, but degrees of freedom, oh, don't forget to write that down as what in this case? 3. Number of categories minus 1. Now this is going to be more ski slopey, isn't it, than the last one? So I'm going to draw so we can see that. Yeah, real ski slopey. Okay, Mrs. Ann Good's technical term there. Look at that. My chi-square, it added these up for me, 9.631. So this is equal to 9.631. And my p-value associated with that is about 0.022. At this university, did I observe some blood types, at least some of them, that were a lot different from what I expected? Yes or no? I did, right? So what do I do with the null hypothesis in this case? Yes. Why am I rejecting? Because p-value is so small. Okay, on to step 4. I'm going to reject that hoe because p is small. Now, what do I believe about the alternative? Do I have evidence or not? I do. So I have evidence to say this is true, okay? And I'm going to put that in context, but I'm going to pause while I write. Okay, so sorry. I'll say it out loud as I'm writing. So I have evidence to say that the actual proportion of blood types among all students at this university is equal to the hypothesized proportions for the whole U.S. Sorry, not equal to, thank you, is not equal to the hypothesized proportion among all in the U.S. Phew. There it is. So I have evidence to say that the actual proportions of blood types among all students at this university is equal to the hypothesized proportions of all U.S. people. Your thoughts, your questions, your inquiries, your desires, any of those.
Yeah, I inquired.